I thank the organizers for giving me this opportunity to present the work, which we recently finished. And also I want to use this opportunity to show the results, and we are going to claim something, and so that claim seems to be bold, but given the finite size systems, this is what we could do, and we would like to get more suggestions on to check with our claim or whatever, in whichever direction. So this is, so the work that I'm going to present is on what we are doing is looking at a system which has some, which shows regular dynamics or chaotic dynamics in the disorder-free limit, and then we introduce disorder, which will break the permutation symmetry of the original Hamiltonian and see how the disorder drives the system. So, and so like yesterday, Professor Vijay Raghavan did mention about these transmons and the fact, and in this paper they discuss that disorder in energies of individual qubit transmons so they claim that if this is there, then the system may be dangerously close to the phase of uncontrollable chaotic fluctuations, which may take the system out of control and we may not be able to do what we want to do. So with this, the plan of the talk is I shall first present the model, the disorder-free model first, discuss the dynamics of this disorder-free model. So this disorder-free model that we study has some semi-classical limit and shows chaos under certain parameter range. And then we go to introducing disorder in this Hamiltonian and study its effects. And what we see is, as I shown during the talk, that there is change in scaling of various quantities that one can show. For example, total angular momentum or the von Neumann entanglement entropy. We see that there is a change in scaling when we increase the strength of disorder from 0 to some value. And the question we ask, is this a phase transition? So that's the plan. So let's go to the main disorder-free Hamiltonian. So this Hamiltonian has an all-to-all interacting term. So along XX direction, so it's all-to-all with equal strength. And then you are also introducing a transverse field, which is periodically kicked. So this Hamiltonian, the disorder-free Hamiltonian, as you can see, that can be rewritten in terms of collective angular momentum operators, where which I define as Jx to be the summation of sigma Ix over all spins. And similarly, one can define Jy and Jz, the collective spin operators. And one can show that this total angular momentum J square is a constant of motion. It commutes with the Hamiltonian. Sorry.
It does not seem to have any rotation symmetry. So why does the total angular momentum quantum number commute?
No, so for example, this would be Jx square, and this is just Jy. And you can check that it commutes.
Maybe we can talk.
Right. So there is this, okay. So now if we start with some total angular momentum J, and we say that the angular momentum is a constant of motion. So during the dynamics, when we evolve the system, one can see that the evolution will always be restricted to a subspace corresponding to the constant J with which we started. And as we can see that there is some, that the Hamiltonian respects the permutation symmetry. Combining all these things, so one more thing is that, so for example, if the total angular momentum quantum number is J, and I rescale my Jx, Jy, Jz with this J, one can show that there is a semi-classical limit, the semi-classical limit exists for this system in the limit J tending to infinity, and we can write the evolution equation as this. So here what it means is the total angular momentum, the scaled angular momentum at n plus 1th kick, how it is related to the values at the nth kick. So this is the semi-classical limit that one can look at. So people have studied this model in and out. So this is the classical, semi-classical limit that we did. And for example, if you start with, so this is the, for example, if you start with some theta phi, initial theta phi, which corresponds to some jx, jy, jz, and evolve the system semi-classically, what we get is, there are these structures depending upon the different values of k, where k is this all-to-all interacting parameter. And what we see is that for small k, there is a predominantly regular dynamics. As I increase k to slightly higher value, what we see is there is a mixed phase. So for example, what it means is that, so if we start from some initial state here, during the evolution, it goes to other theta phis. So this is a mix, but on the other hand, if you start from some state here, during the evolution, it is restricted within the region. So this is the, and if I go to, say, for example, even larger k values, the system seems to be predominantly chaotic. So this is the semi-classical limit results. And so we can see that in that semi-classical limit, as you increase k, the system shows transition from, or change in dynamics from predominantly regular to predominantly chaotic. Now, so this is done for very large system sizes. On the other hand, if I reduce the number of spins, I can still do some, I can evolve the system using quantum dynamics. So in order to compare what we have in the previous figure, where you start from some total angular momentum j and theta phi, if I want to compare, I can also, the best way would be to start from a spin coherent state.
Sorry, just a question about the classical case. Can you go back to the equations, the map? So, no. So, what is the setup? Is one large spin? It's just one.
It's a one top.
One top.
Correct.
And
with the total jx, jy, jz.
Right. And if you go next, so this the mixed phase space. The next. So when it's mixed, can you increase something to make it more chaotic, or is it where k equal to 3, it remains mixed no matter what, or can you change something else here?
No. So it remains mixed if for k equal to 3. What other thing do you have in mind?
Okay, so there's no other parameter, right? There's no other.
Tau. Oh yeah, this.
I see.
So we have fixed the p here.
Yeah.
To be pi by 2.
Yeah.
Because in that limit, these equations look simple. But even for non-p, we can write some equations.
So for any angle, it is going to be mixed at k equal to 3.
No. So that it depends.
That depends.
So here we have made it p equal to pi by 2, and this is for p equal to pi by 2. The result is for p equal to pi by 2.
No. For my question is there some angle where there is no mixed phase space at all? Or is there always a mixed phase space?
So yes, there will.
It may happen at some other k, but there is always a mixed phase space.
Yes.
Okay, thanks.
So yes. Large scale limit, yes.
So you just have this correction in the.
Can you neglect second term?
Because in the large scale limit, in principle, we know exactly how to.
No. We need these kicks to take it to the chaotic. Yes.
So sorry. So yeah. So exactly. So yeah. So there will be a periodicity. So you can't go. I mean, the semi-classical limit is not defined for fixed n and large k. So n should also be going to infinity for this to make sense. Yeah.
Yes.
Yeah.
Okay. So in order to compare, what we can do is we start from some spin coherent state defined like this. So the reason is that one can check that the expectation value of jx, jy, jz in this spin coherent state corresponds to our j cos theta j sin theta cos phi, j sin theta sin phi. So now this initial state, which we are going to evolve using that disorder-free Hamiltonian, we can see that it is permutationally symmetric, where the total angular momentum is, so this quantum number, as you can see, should be n by 2, so that j square is always equal to this value, j into j plus 1, and it is always constant during the dynamics. So this is the setup. So, and because this is a periodically kicked Hamiltonian, we can use Floquet dynamics to write the state at nth, after nth kick to be the u to the power n times the initial state, spin coherent state theta phi. And as I said, for this theta phi, our j angular momentum is n by 2, and it will go to all these 2j plus 1 different values during the dynamics, keeping the j constant. And these 2j plus 1 values, that means during the evolution, the Hamiltonian or the system explores this n plus 1 dimensions. And we can look at, for example, some quantities. We looked at linear entropy, and which is defined as 1 minus, this is the reduced density matrix of q qubits, and it is 1 minus, so we can see that, so this is the definition of linear entropy, and setting q equal to 1, if we start with different initial states and calculate this linear entropy, so this is calculated over large times, and we plot it, we see that there is some similarity of the structure that we get with the classical phase space. So this is the spin coherent state theta phi. So you start from a spin coherent state for a given theta and phi, evolve it, calculate the linear entropy, and just plot it here. Yeah, so this is a theta phi. Correct. Yes. So for example, here, so yeah, there in the mixed phase. So we do see that the linear entropy is small, close to these regions, which corresponds to our regular points in the k equal to 3 there. So we do see some similarities. So some people do say that the regular region might have smaller entropy compared to the chaotic point, and that is being captured here. For example, this is some 0.3 in this regular region, and this on the green part corresponds to 0.44. So there is, so you have a higher entropy in the region corresponding to the chaotic part and smaller one corresponding to the, so this is the setup, and now let's go to introducing the disorder. So what we know is so far that the disorder-free Hamiltonian conserves the total angular momentum, and that the dynamics is always restricted within the n plus 1 dimensions. But now if I introduce the disorder, so the disorder is introduced in the all-to-all interacting term, and this value epsilon LL prime, site-dependent LL prime, it's taken from some normal distribution with 0 mean, and sorry, this is W because I'm using W in the rest of the slides. So variance W. And so now if you look at the dynamics, what we know is J square will no longer be n by 2 into n by 2 plus 1, but it's going to decrease. And we expect that the system will now go to the full, will explore the full Hilbert space 2 to the power n of n 2 to the power n dimensions. So before actually we do the numerics, or I show the results of the numerics, I also want to do some, discuss this results in the special case of p equal to 0 limit. That is, I don't have any kicks. And then in the absence of the kicks, how does the disorder takes the evolution? And it's interesting in the sense that in this p equal to 0 limit, we can calculate these expectation values of jx square, jy square, jz square. And one can show that the total angular momentum j square evolves like this. If you look at this expression, what we see is that the j square, so clearly for large time, it reaches to some time independent values because it exponentially decreases here. So this goes to 0. and at large times it goes to some constant value. This constant value is also dependent, is a function of theta and phi, that means my initial state. Another point to note here is that this j square, for certain theta phi values, for example, theta equal to 0 and any value of phi, or phi equal to pi by 2 and any value of theta. So theta equal to 0 and any, is some z axis, with theta equal to 0 or phi equal to 0 corresponds to all spins along z axis. Remember, our Hamiltonian is all to all interacting along x direction with a field in y. And so for certain initial states, for example, theta 0 and any value of phi, what we see is that j square goes to a value which is 3n by 4. And this 3n by 4 has a special significance that we will see later. So for certain theta phi values, j square saturates to 3n by 4. But for all the other theta phi values, in the case where you don't have any kicks, what we find is that it saturates to some value of j square which scales as n square. It still scales as n square. Only for certain values this goes to linearly with n. And so the importance we'll discuss later. This 3n by 4 is also the j square that you get when you calculate it using random matrix theory. So that I'll come later. So this has a significance in our later discussions. But so a plot of this would be that if I take two different disorder strengths, I see that the saturation value is independent of the disorder strength, and I should have added also that this is for some initial theta and phi values. If I change my theta phi values, this saturates to some other value, as also predicted by the analytical expression. So, and this is the 3n by 4. For n equal to 12, this is the 3n by 4 value. And as we see, this is slightly, not slightly, it's above the RMT value. So yes, so this is the thing, without kicks, j square saturates to some disorder independent value, and this value is not related to some 3n by 4. So you can't get 3n by 4, or 3n by 4 is actually the value that you get using random matrix theory, which we discuss later. So now, as I said, we'll focus this talk essentially with p equal to pi by 2. We are fixing the kicking strength to be p equal to pi by 2, the factor in front of the kick, and ask this question. So now I have introduced the disorder. I know that initially without the disorder, the system was within this n+1 dimensions. But now when I introduce the disorder, the system goes to the 2 to the power n full space. And we can analyze this whole change in the dynamics looking at different quantities. One of them would be to ask the question, how much is the system within the permutation symmetric subspace? So for example, I evolve this wave function over different kicks, and then calculate a quantity called overlap, which just takes the which is just the overlap of the evolved state with these permutation symmetric states. And we can generate these n+1 permutation symmetric states by saying that these are the n+1 states that you get by looking at no downspins, then a linear combination of one downspin, linear combination of two downspins, and similarly all downspins. So you get all these n+1 permutation symmetric subspace. You just take the overlap and see how the system, as it evolves in presence of disorder, goes out of the permutation symmetric subspace, because we know it is going to go out. How it goes out, that one can look at. So we studied this overlap. So this is what we have plotted: overlap as a function of time. This is the nth kick. And what we see is that, for example, if the disorder is very small, overlap is close to 1. That means it stays more or less within the permutation symmetric subspace. Then when I'm increasing the disorder, the overlap decreases, and the overlap goes to 0 at large times for very large disorder. So this is 5.0. So it goes to 0 at large disorder. This, the plot on the right hand side is looking at the saturated values of the overlap for different W's as a function of W for different K values. So for example, K equal to 1, if you look at the disorder free part, K equal to 1 was the regular region. And we see that for K equal to 1, your overlap up to a disorder strength of 1 has decreased only to some value close to 80%. On the other hand, when K is 6, that means my original disorder free Hamiltonian is chaotic. In that limit, if I introduce disorder, then I see that the overlap with the permutation symmetric subspace is actually 0. And it goes to 0 faster as you go more and more to the chaotic disorder free limit. So this is one way to look at the dynamics. The other quantity that one can study to understand how the disorder affects the evolution is to look at the total angular momentum. So I know that in the disorder free limit, the total angular momentum J square is simply n by 2 into n by 2 plus 1, but it is going to decrease or because it's going to explore other J values also. Since J square is no longer a constant of motion, it's going to decrease. And this figure essentially shows the effect of disorder on the evolution of J square. So clearly, this is n equal to 12. So for 0 disorder, it's constant. So it's always n by 2 into n by 2 plus 1. As I increase the disorder, J square decreases, but slightly. Then this corresponds to the disorder strength 2, 2.6, and then 5. Now, so for large disorder, we see that it saturates to some value, and I'll discuss this value in the next slide. But we do see that there is a value J square. Beyond this, for very large disorder, we always see that the J square saturates to this value, which is RMT, and this actually is the 3n by 4 that we had seen in the previous slides. This is just to show J square as a function of W for one particular K, the saturation values for different Ws, and it goes to, for large W, it goes to some value 3n by 4, and these are obtained by averaging over disorder and also time. Oh, one important thing that I should mention here is, if you look at these vertical lines also actually captures the change of dynamics from permutation symmetric to the full Hilbert space. So for example, this is the time step corresponding to n plus 1. So I have n is equal to 12. So this is roughly around 15, where you see that there is a first level of saturation or steady state that is coming. So this is the Heisenberg time scale corresponding to the n plus 1 dimension dynamics. On the other hand, this vertical line corresponds to 2 to the power n, so 2 to the power 12 value. So this is the second time scale coming into the picture where the system goes to another steady state, and we are looking at the steady state values after it crosses the Heisenberg scale, time scale corresponding to the full Hilbert space. So, so this is J square.
Sorry, just one second.
Yeah.
So this 3n by 4, when does it go to 3n by 4? At
large W. So I'll come to that in a minute. But 3n by 4 is the value that one gets in the limit of large W, large disorder.
Okay, okay. Can you go to the previous slide? In the right plot, suppose in principle I increase n.
You increase n.
N. Or let's say decrease n. Just as a trend, how when I increase n, is this does this become sharper or?
Yes, yes. We do see sharper.
So there is some critical disorder?
Our claim is that, so that's what I'm going to show. That there is a critical disorder where there is a phase transition. So
I see. Okay, okay.
Right. 3n, as in the value is 3n by 4. Oh, yeah, yeah. So for large W, it is fixed, but for other Ws, it is capital N also it changes. It's different.
So if I just subtract 3n by 4, you see nice collapse. There's a nice critical point. Is that the claim?
Yeah. So yeah, we do some finite size scaling and not subtracting 3n by 4, but yeah, we use J square and some other, for example, von Neumann entropy to show that there is a crossing.
Okay, thanks.
So yeah, this is just to compare the P equal to 0. That means disorder without kicks, for which we had a nice analytical expression, and disorder with kicks. And so for example, disorder with kicks depends, the saturation value depends on W. On the other hand, without kicks, it doesn't depend on the value of the disorder. As we saw, it exponentially was decreasing for the P equal to 0 limit. Now, yeah, one more point. So we studied the overlap, we studied J square. The other quantity that we have studied is this von Neumann entropy, which is defined. We have been hearing this throughout the meeting, and that is so you take a reduced density matrix of Q qubits, calculate the von Neumann entropy, and we have set Q equal to n by 2 for all our discussions. And what we see is that here also, as W is increasing, we see that this Sn by 2 goes to some constant value. Again, this corresponds to the von Neumann entropy that one gets using the random matrix theory. And so these are for von Neumann entropy as a function of time. And this is the time average, disorder average value, von Neumann entropy as a function of W. So you are looking at the saturated values. Here also we see the two time scales that we saw in the evolution of J square, which are roughly of the order of n plus 1 here and 2 to the power n, 2 to the power system size here. Okay, so now this is what I've been telling, that what we find is that in the limit of large disorder, one can actually calculate, for example, J square using the random matrix theory. And in the full Hilbert space, so this is, if you calculate random matrix theory in 2 to the power n dimensional space, one can show that J square is actually equal to 3n by 4. And this is what we are seeing in our dynamics also, that no matter what we do for large disorder, these expectation values are going to the values given by the random matrix theory in the full Hilbert space. Similarly, this is a well-known result for von Neumann entropy. Random matrix theory has this value for full 2 to the power n dimensions. So what we see essentially is in the disorder free limit or small disorder, J square is going as n by 2 into n by 2 plus 1, or of the order of n square. On the other hand, when I increase the disorder to large values, this J square is going to a value which is linearly increasing with n. Similarly, von Neumann entropy in the permutation, this von Neumann entropy is known, so it's not something that we have done. So von Neumann entropy goes logarithmically with the system size when the dynamics is within the permutation symmetric subspace. This is well studied. And on the other hand, in the full Hilbert space, it goes as n by 2 minus this. So we see that there is a change in scaling of various quantities with the system size when we increase the disorder. And this is what we are focusing, that whether, so now we ask this question. So this is again showing the scaling. We have checked this, that for W equal to 0, or the red line is the permutation symmetric expression for J square, which is n by W equal to 0, we know it is n by 2 into n by 2 plus 1, so that's this. And for very large W, it goes as 3n by 4, that is this black line. And this black line is the analytical expression, the triangles are the numerics, and it matches that this goes as 3n by 4 and that one goes as n by 2 into n by 2 plus 1. Same thing we have done for von Neumann entropy also, and we see that there is a change from log n to n by 2 as we increase the disorder. Okay, so now the question that if there is a change in scaling then whether there is some sort of phase transition happening in the system. And this is what we get. So we we fit this J square to some finite size scaling expression. And we could only go up to system size of the order of 16. But with this system size, we do find that, so this is the result for when your parameter k is equal to 1, that means your disorder free limit is in the regular region. I'm using the same theta phi which I've been discussing, which is some 2.25 and 1.1. That's the initial state. And what we see is that if I do this finite size scaling, there seems to be a crossing at the WC, which is close to 2.3. With nu, roughly all our simulations show that nu is of the order of this zeta, and nu, the value of nu in this particular case is 0.6. And we use the collapse of the figure to demonstrate that to demonstrate the validity of these values which we get using finite size scaling. Now, so this is all done with k equal to 1. Obviously the next question to ask is what happens when I change my k value? That means I go more and more towards the chaotic region of my disorder free Hamiltonian. And so does it work for other k as well, meaning is there a phase transition for other k values? Intuitively, I mean, if there is a phase transition, intuitively what we expect is that if you are going more and more into the chaotic limit, then the amount of disorder that is required to take the system out of the permutation symmetric subspace, full Hilbert space, towards the random matrix theory, the expectation is that the strength of the disorder should be smaller. And so this is what we get for higher value of k. And okay, and higher value of, so this is the collapse figure for k equal to 2, and we did did the finite size scaling for other k values, and we see that the WC decreases as k increases. The exponents are not constant, as in there is some dependence of these new zeta exponents on the k values. Yeah, that's the, yeah. So more or less we find that zeta is of the order of nu, except some. And yeah, so these are the WC and that we get using finite size scaling. So observations is that WC decreases as chaos parameter increases. Critical exponents depend upon k values. So if you look at it, there is a change from, there is a range between 0.3 to 0.6. This is when we do for different k values, but all of them we have done calculations for the same initial state theta phi. The next question that one can ask is what happens when you change the initial state also, because as you saw in the disorder free limit, your nature of this, the initial state has different properties for different k values. So what if I change the initial state? So what we have done is the state that I have been talking about till now is that this black triangle. So this is the theta phi that I have been using, that I have used to discuss the results so far. We can explore other theta phi or other initial conditions in the phase space and see whether what do we get. For example, this corresponds to the pink or this initial state. Again, we get, so for if you remember, for the black triangle that I discussed, the WC was 2.3 and nu and zeta were roughly of the same value. So it's 0.6 plus minus 0.02. So we see that for this initial state, the WC, nu, zeta are within the error bar and they are same. So the pink and the black, they show similar scaling behavior. So also, so this is the yellow. So this is the next point that I'm discussing, the yellow point. Here also we see that, so the collapse is done only for 12, 14 and 16. We see that WC is of the same order as your black, pink and yellow. Nu and zeta are also, at least to me, they are same. But the problem is this: if we start from green, which is the corresponding to pi by 2, which is all along. So pi by 2 means my initial state is along y direction. If I start, and this actually, this point in my classical phase space is a fixed point in the sense that if I, in the disorder free limit, if I start the system from this pi by 2, it remains there. So, but for this point, somehow we are not getting any scaling, but it's not at all good, as in but still, if I just force myself, there is a WC which is different from my previous values, but one can still argue the decrease in WC for values like for an initial state which is pi by 2, because this is, this initial state is all along y direction and the disorder is in the XX interaction term. So, so in some sense, this initial state is highly coherent in the in terms of the disorder interaction direction, and so you need relatively less disorder to take it into the full Hilbert space RMT thing. So one can argue why WC is small, but definitely whether there is a WC in this particular case, it's not very clear, but at least yeah, so there is not a good, that also could be because it's a fixed point of the initial, so we don't understand completely this thing. But otherwise, even for the red point, which is close to the fixed point, we do see scaling, and the WC is close to the 1.2 value. That also could be because it is close to my pi by 2 initial state. Okay, so this is, we did this analysis using for using J square quantity. One can also redo all these things for von Neumann entropy, and we do see collapse with some WC which is actually smaller than what we get for my J square, but this is what it is. Okay, so I'm concluding by saying that this what we have done is study the effect of introducing disorder in the dynamics of this kicked top, and so we essentially study how it goes out of the permutation symmetric subspace, how J square decreases, and what is the, we looked at the change in scaling of J square and von Neumann entropy. Finally, the finite size scaling with system sizes of the order of 16 indicates a second order phase transition, but yeah, it's all within the finite size errors also. So with this, I conclude. Thank you.
Yeah, so two things. You can also presumably look for the transition by looking at the level spacing statistics of the Floquet Hamiltonian.
Yes, so I have it here, although, so what we do see is that, for example, W equal, this is the statistics for W equal to 1.5, which is less than the critical strength, which was 2.3, and we do see Poisson. On the other hand, when W is 4, we see this GOE.
Right. Yeah, but I'm saying that you can sort of do something a little more systematic, which is from the level spacing statistics, you can maybe extract this number, which is called the ratio of successive gaps.
Correct, yes.
And then calculate, I mean, instead of obtaining the full distribution, that number as a function of W, and see where it crosses over from some random matrix value to a Poisson value. So that was one comment. The other one is, so what you've done here is you've held in your calculations the kicking strength to be a constant, and you have changed the value of the disorder to look for a transition. You could presumably also do it the other way, right? I mean, you could hold the value of the disorder fixed, and then as you increase the kicking strength, you would expect to go into a chaotic phase. Right. And so I just wonder if you've looked at that and maybe tried to extract any exponents, I mean, do you actually see any nice sort of crossing of these curves? Can you extract an exponent if you go in that direction?
We haven't done that, fixing the disorder and change the K, but we can have a look at it.
Hi. So maybe this is a bit of a vague question, but so if I increase n, right?
System
Size. So basically in large n limit, I should reach the classical limit, right? Is that correct? I mean, if I take the larger limit of this quantum system,
I know the classical limit for the disorder free, and yes.
you should reach, even with disorder, I guess, you should reach the classical, some classical
Some limit,
disordered
yes,
system.
Could be, yes.
So in principle, if you do the classical disordered system, do you see this transition? Because in some sense, if you take the larger limit of this quantum model, you should see, if you see a transition, that means that the classical model might have this transition. So is that something that you
So what you're saying is that look at the classical limit of this disordered Hamiltonian.
Yeah.
And
Because
whether that has a
transition. Because if the larger limit, I mean, larger limit of these models are typically, they have a classical limit, and you will, so if the classical limit does not have this transition, then maybe this is a finite n effect, and maybe,
I see.
Yeah. No, actually here, when there is no disorder, there are these collective variables or some kind of mean field things, right? That is the classical limit. So once you have introduced disorder, these are really just a collection of spin half particles. There is no well-defined classical limit in the disorder free, unless you are talking about increasing the spin of each of these things from half to something else, some large. So that will be a collection of large spin.
Okay.
But as it is here, it would be like something like, classical limit of a transverse field Ising model.
Yeah, okay, so I got it.
It's not well defined.
So there's no classical limit of this,
no,
unless you increase the local Hilbert space or something, right? But okay, that's a different, okay. So there's no way to check this.
No, there is no classical,
I see.
there's no classical picture. Although interestingly, the classical picture approximately holds for small, disorder, because it's not escaping from the permutation symmetric subspace for even small disorder. So there is some effective collective variable. But that is really an approximation and only for small disorder.
The size of the local spin, that will be very hard to do, right?
Yeah.
So that is
right. It's interesting, but yeah. Even in the disorder-free case, actually, that is, I don't know what, like a Q-trit equivalent of the kick top.
Okay.
I don't know.
Just one more question. If you go to the linear entropy plot, so
Scaling.
Yeah.
Or the evolution.
The
linear entropy.
Linear entropy.
Sorry,
linear.
okay.
So but if you go to the classical plot first in previous slides, so here, if I see these things, it's reasonably clear which is mixed and which is fully chaotic.
Yes.
But if I see the linear entropy plot, I mean, they all seem to look more or less, if I see those two linear entropy plots on the right side, it's very hard for me to make a judgment, right? So how do you...
I'm not making any comment. Only thing I'm saying is that, yes, in the classical limit, where you had regular regions in the classical limit, there is a slightly smaller entanglement entropy compared to the...
Uma, what is the number of qubits here? What is J?
Must be 12.
So it's a very small J. So,
J.
It's not really in the semi-classical regime.
Right.
It's, So you're seeing, H bar is large. So you're having all kinds of quantum effects.
Yes, so we
do some random matrix diagnostics, you'll get some intermediate statistics or something. Is that, does that happen?
It's a very small Hilbert space. It's only 13-dimensional Hilbert space.
Okay.
So you won't even get good statistics.
Okay.
But if you go to large J, and which you can easily do in the permutation symmetric thing, you will see much more clearer pictures.
But in that case, if you do spectral analysis, you will see neither random matrix nor...
Exactly. You will see intermediate, Brody, and so on.
Okay. Thanks.
Any other questions? If not, let's thank Uma again.